I trust God that we had a refreshing night rest. This morning we are going to be going into autocorrelation function and partial autocorrelation function for some time series processes. So a time series is made up of sequence of observations that are recorded at regular intervals. And when you have sequence of observations, usually there is a strong autocorrelation between observed data and past values. So autocorrelation function is a function that helps us understand the strengths and correlation between observations and their past values. In an autocorrelation, we have the autocovariance, because as events change over time, in some time series data, the change over time is dynamic. And for us to be able to model or carry out prediction, we need to be able to get a stationary state where the change over time in the mean, in the variance are constant, so that predictions can be made. And two major properties about a time series data is that, one, we have to check for stationarity, and then the change in variance over time, which is the trend. So autocorrelation, as shown, I want to look at the covariance. The covariance function is defined as yt of s, where t is the current observation point, and s is in time, ys is the observation point in the past or the last value. So the covariance, when we compare the covariance, that's the correlation or the relationship strength, the variance over time in the trend between the present observation and the last lag of value. We carry out, we do the expected, what is the expectation between y and s over time. Okay, so this gives us the covariance between values at time t and s for a time series. So if we have this covariance and want to get the covariance between the present observation and the past value, the expected outcome we look at the time series of the observation and compare it with the mean. So what is the change over time in the observation with its mean, and the change over time of the last lag value to its mean? And this, if we expand this, we have Please, media, please show the board. So if we expand this expression, we have this, and this we cancel. So at the end of the day, we have okay. So we have the expression in the slide. This gives us the variance between the values at time t of the observed data and the time of its lag or the past value. So the autocorrelation function is defined as the correlation where we have the covariance between the observed value and its past value or at a time lag all over the standard deviation of the present observation and its past value. So sigma t sigma s is the standard deviation of the time series yt, the present point in the data and the past observation. This gives the correlation between the values at time t and s for a time series. So it can also be expressed in this way, where the autocorrelation function is rewritten as this. So k is the time lag to the observed points. So for example, when we are trying to compare, we have a time series data, a monthly data, and we are trying to see if the increase in the cases in, for instance, in January resulted in increase in cases in May. So we are trying to compare, we are trying to compare and see if, based on what happened in January, we can predict what will happen in May. So autocorrelation helps us to bring out the relationship, the correlation within this data, the change of variance over time in the trend, and then to be able to derive a stationary time series where it will be safe to make predictions, where we have constant variance over time. So this gives the variance between values at time t and t plus k for a time series. And the autocorrelation is written as this, where we have the covariance all over the standard deviations, giving us the correlation between the values at time t and t plus k for a time series. Now, like I said, time series, when we want to deal with the autocorrelation, the point is to observe the variance over time and then what steps to take to obtain a stationary process. So one of the properties of an ACF is that we want a stationary process in which the covariance at the present observation has a mean value or the same value, constant value as the lag point, where we have the same value of covariance at the lag or past value point. Also, when we take the absolute value of the covariance, we want it to be within the range of 1, less than or equal to 1, like we have in the graph of an ACF plot. Yes, so like this plot here, we have autocorrelation where we want a case where the absolute values in the correlation relationships are within the, the interval where we have the blue lines. So we want a case where they are within this cutoff. So for this time series, the first autocorrelation plot, you can see that we've not achieved that. This is another ACF plot of another time series. We see that for this time series, they are almost close to the absolute value points. So also another thing is non-uniqueness. The desired property is that a stationary normal process is completely determined by its mean, its variance, and the ACF. However, there are non-normal processes with the same ACF. There are sometimes when we have a non-stationary data that the ACF may look like, may have the same pattern as a data that might be stationary. So further analysis will be carried out to determine the actual uniqueness of the stationarity. So autocorrelation function or autocovariance is characterized by the first and second moments. It's characterized by the first and second moments, where the first moment is the mean and the second moment the variance between these two points in data we are comparing. The present points compared to the lag or the past data points in time. So the underlying distribution is normal when we are able to achieve these properties. We have an ACF of purely random process or Gaussian white noise given by the variance being within the range of being 1 when k is equal to 0 and being 0 otherwise. When we have a time series, there's always fluctuations. Okay, so when we are able to achieve stationarity is when we have the time series having a stationary variance over time, regardless of the fluctuations of the Gaussian distribution. So when the correlation is carried out between the present observation and itself, we have the covariance to be 1. So k is 0, that is, there's no time lag. We are comparing it between itself. But when you are comparing it between its past value, we get a 0. So k could be the time lag you give may be more than 1, could be 2, could be 3. So white noise refers to a collection of random fluctuations. So for every time series, when you have data you've collected at constant time intervals over time, there is always a tendency that there will be strong correlation, especially when you are collecting your data regularly, when you are not having so many missing values or poor recording. There would be some level of correlation. And so to be able to, when you plot the time series, you see the fluctuation, the peaks and the lows. But to be able to achieve stationarity, where we have a pure white noise or Gaussian distribution, the white noise refers to the collection of the random fluctuations. So if you apply a distribution to the white noise, it becomes Gaussian white noise, a standard white noise process with a Gaussian distribution. Here I want to look at an example of an ACF of lag K. Sorry, that's lag K. So let y1, y2, yn be the observed time series. It could be a record of cases of a disease for some years. Okay, so you have your different data points in January, y1, February, y2, March, y3, and so on to the end of the data. So the ACF at lag K can be approximated as expressed here, where the numerator is the covariance and the denominator is the standard deviation. So the simple ACF at lag K is given as this, where the numerator is the covariance and the denominator is the variance. So the mean and the variance are constant throughout any K. So our target is to ensure that we achieve a constant covariance and we achieve a constant mean and variance over time. And the lag is dependent on the point time which you want to compare. So for a correlogram of ACF plots, like the plot I showed before, the graph is usually plotted as RK against K. The ACF plays an important role in model identification. So when we have an ACF plot, so it is plotted as the covariance over time with respect to the lag. K is the lag. I have the cutoff where we want to use to determine the stationarity. So when we plot the ACF, the point at which the correlation over time is within this threshold, then that's the point where we can begin to talk of stationarity. So when you have a time series data and you plot it initially using the ACF plot, to be able to determine the parameters of your ARIMA, where we have the autoregression, the difference, and the moving average. We have P, the autoregression part, D is the difference, and Q is the moving average. Okay, so the point at which you have the autocorrelation within the cutoff of the threshold cutoff line, it can serve as your first point of P. And then we also carry out the PACF The PACF is a partial differentiation between the time points within your observed data and the past events. For instance, you have a data where you've carried out autocorrelation between March and January. Okay, so from you got the autocorrelation between March and January, and you got the autocorrelation between May and March. So when you want to get the direct relationship between May and January, that is where our PACF comes in. To get direct relationships between covariance within the observed data, so that there's no point that will be left unaccounted for, to be ensured that at the end of the day every hidden pattern is taken care of. So the partial autocorrelation function of order k, noted as alpha k, is the partial correlation coefficient between an observation and its past value at a certain time lag after conditioning on the intermediate values of the process. So this is the expression of the partial correlation coefficient between an observation and its past value after conditioning it. Okay, so for the model identification, the structure of the PACF and the ACF and the ACF plots can help us identify underlying model. So let's go to our R and do some autocorrelation function plots. So I believe we all have the AirPassenger data. So if you can call your AirPassenger data again, I decided to save mine into a variable name called data_tree. So let's run that line of code in our R. AirPassenger, want to call the data or the time series AirPassenger, and you can save it in a variable name you prefer. All right, so I believe we are already familiar with that. Have we done that? Okay, so some of you, your R may just be waking up for the day, so you have to ensure that you rerun some of your libraries again if you have libraries there, but we don't really need a library for this one. So you just call in the AirPassenger data. So let's wait for those that are setting up their R. Yes. Okay. Okay, so after you call in your AirPassenger data, line 4 of my R, it's about preparing it for the time series process. So that line helps you set the format of your data in a time series format. So TS there means time series. You have the data, and then you have the date part. So the data started from 19 49. If you want to verify that, you can just say data underscore tree. Since we have saved air passenger data into data underscore tree, so if we now run data underscore tree, we will see the air passenger data. So from there, you can determine the time it started. So the record started from 1949. So for you to set your data as a time series format, you need to know the start date. So 1949 is the year and 1 is the month, which is January, because the record started in January. So if your data were daily data, you have to add extra comma here and 1. That okay, the first day in the month of January in 1949. But our data is monthly data, so we just put the year and the month. Then the frequency is 12 because every year stops at the 12th month. So if it was a weekly data, your frequency would be like 52, because in a year we have 52 weeks. But in a year we have 12 months. That's why we have our frequency as 12. Okay, so when you set the format of the time series data, the next thing is to plot the ACF. So okay, so sorry. So for your groups that have data, you can also try it out. You try to know the start point of your data, the year, and the format. If it's a weekly data, if it's a monthly data, or a daily data. Some may add the endpoint too, but for this stage, it's not necessary you add the last year point, which is 1960. That point is what matters. Are we done with setting the format of time series? Okay, so next to plot the ACF, we are going ahead of us. To plot the ACF, call the data, and then we give it a label, ACF of this data, and lag.max. That means the lag points that you want to compare the data with. At what point do you want the comparison to be? So most times we use lag 10. Yeah, the lag tells you the point in time you are comparing your data. You want to compare it after every 10 time points. After every 10 time points, according to your data. Okay, so if you run that line, you have the initial ACF of the data, the moving average over time in lag, and we can see that they are not within the required cutoff. But let's go ahead and look at also the PACF over time. So the PACF, we also follow the same format, but here we are using the PACF. So if you run the PACF of the same data at the same time lag, we have this. It's more of the partial correlation. So now, based on that, looking at the ACF and PACF, we are not certain that this is stationary, because the ACF is, the autocorrelation is so strong in the data, and so we don't know if this is stationary. So for further analysis, we carry out the ADF test. This test is to check if the p-value of the data is less than 0.05, which will let us know that actually our data is now within a stationary point. Yes. So you're supposed to actually install some packages to be able to do that ADF. So the one of the package we need is the T-series package and the forecast package. So I'm coming. So if you have called those libraries, you have to call the library. Since you are just opening your R today, if you have called them, then you go back and run your ADF test on the data, the augmented Dickey-Fuller test. So from the p-value, you can see that we are having 0.01, which is less than 0.05. When you run the ADF, the result. So depending on your own data, it will give you the p-value. So when you have a p-value smaller than the threshold 0.05, you have achieved the stationary data. Then you can move on. Don't need to do differencing, which is the D in our ARIMA. But if the p-value was greater than that, you can see my code. I put hashtag to deactivate these two lines of code. So assuming the p-value was higher than 0.05, I'll have to run this line where I'll do a first differencing of the data. Huh? Yes, I'm coming. Okay, so if you are dealing with a time series data of which after you ran the ADF test for the first time, the p-value was not less than 0.05, then your data is not yet stationary. So it's not yet a good point to carry out your ARIMA or to determine your ARIMA model parameters and then carry out your forecast. So you still need to do some differencing to the data. And do that, here, I differentiated the data tree, which contains my AirPassenger data. I differentiated it and saved it in a variable name called case 1 d1, case 1 underscore d1. So the difference value is now in case 1 difference 1. So I will now repeat the ACF test on it to confirm if it is now stationary after one differencing. If after one differencing the p-value is still not yet less than 0.01, I have to do a second differencing. Okay, so that means for the second differencing, okay, I'll go over it again, but let me just, so assuming we want to do a second differencing, we have to now say, okay, let's call this second differencing. And what we are differencing now is the result. It's the first differencing, we want to give it a second differencing. And then we have to still check the test again. Is it now stationary or not? Okay, so the data determines how many differencing you will do. If the data at the first stage, line 14, at the first augmented degree Fuller test, p-value result, where you have here your console, see that when you run the Fuller test, it brings out some results. So you check for this p-value. Okay. If it's less than 0.05. Usually, if it's not less than 0.05, not have this red message. So this red message tells us that the p-value is smaller than 0.05. So that tells us that we are now in the stationary data. Okay. So this alternative hypothesis stationary does not mean your data is stationary. It's just telling you that depending on the p-value you get, you choose which hypothesis you want. That is, it is stationary or non-stationary. Yes. So I did not expect you to do a second differencing for this data, because when we tested it, in fact, you're not supposed to do any differencing for this data, because right from the first test, the first ACF test, the p-value was already lower than 0.05. 0.05, yes. So for this second example, just follow. You may not have the data. So now this data, I have it saved, and I read it into something like monthly data. Now, this monthly data, want to see what is inside. Okay, okay. The ACF. Let's go over the air passenger data again. So now when you have a data and you read it in, you save it in a variable, because whatever you want to use in R must be saved within the R environment. So we created a variable name called data underscore tree and saved the data there. Line 6 is just to view the content of the data. Okay, and sometimes it helps you to be able to view the start time of the data when you are trying to format your data as a time series. So after viewing it, I can see that the start point is the 1949 and it's a monthly data. So that's why I have my start as C 1949 1. And it's a yearly that it comes after year by year. So I keep the frequency as 12. If it's a weekly data, your time series definition will have other added parameters, like I said. You have to change the frequency and all that. So now you go ahead to check the autocorrelation function of the data compared to its lag, and here we chose to use a maximum lag of 10. And we also carried out the PACF comparison. So after doing that, the plot gave us an insight to what the data looks like. The correlation, we can see that there are strong correlation in the data over time, but in the PACF, we observe a good within the cutoff. So to ensure that your data is actually stationary, carry out the ADF test. ADF test help us to calculate the p-value, threshold at which you obtain stationarity, which must be less than 0.05. And so when we did that, the p-value we got was less than. So there was no need to do further differencing. Okay, so this second time series data I have here, we want to see whether this data set will require further differencing or not. Okay, so I read the data, you can just follow. Reading the data, you can decide to view the content of the data. So the content of my data here is this, and the name of the columns are month and total cases. Okay, so now data 3, I want to bring out the column I need, which is the total cases. So I said month underscore dollar total. That is, in this variable location called monthly data, choose the column titled total, the column having the cases. Then I put it in time series format because from the data it's in monthly format. So I have the year, the start year, which was 2019, and then January. Okay. So now I carry out the ACF. You can see that in the ACF of this one, there's no much strong correlation. The values are almost very close to the cutoff. And then the PACF, there are varieties there, but within the cutoff from the beginning. So now let's do the ADF test to actually confirm stationarity. So from the ADF test, you see the p-value. Although it's telling us this, but it's not yet stationary. Okay, that's not giving us the message that it is below the PV. So we carry out one differencing. Okay, the code, you've written the code before. So I carried out the ADF test. Okay, so this is when you are reading in a data. Maybe you have the data saved in your laptop. And for you to successfully read any data in, you must have read the path. You can say I have a path. So the path or the location where the data is saved, I have to run it so that when I now tell R to read it, it will be able to locate it. Okay? So now you read in the data, then you look at the data, you pick the column. Some data may have various columns, may have various features there, but the feature of interest, especially in disease data, we are mostly interested in confirmed cases. So in this case, the confirmed cases are in the total are called total. Okay, because we aggregated a weekly data to monthly data. So you call out the column of the confirmed cases. and then put it in a time series format, carry out the ACF and PACF analysis, as well as carry out the augmented Diggin-Fuller test to confirm stationarity. If the data is not conforming to stationarity, then you have to do differencing. So the number of differencing you do dependent on the nature of the data, the point at which it becomes below the required p-value threshold. I'm going to stop at this point this morning. Thank you for your attention.